everyone. Today we're talking once again about MIDI. Let me show you my latest synthesizer. At the start of this project, I got a message from a man named Aaron Andrew Hunt, and he'd seen my synth cable and my world's smallest MIDI synthesizer, and he'd recognized the greatness here. I mean, they sound pretty terrible, but they're such a great gimmick. I mean, come on, it's the world's smallest MIDI synthesizer. So Aaron had an idea. He said to me, what if we built one of these, but made it good? What if we had a budget and put some real engineering into it? What if we made it a real synthesizer? So what do we mean by a real synthesizer? Well, we want it to be fully polyphonic, at least 16 voices. We want full resolution pitch bend. None of this half-ass bend stuff. We want 14-bit bend value, and we want adjustable range per channel. We want envelopes. We want different waveforms. We want dual oscillators, quad oscillators. We want 44 kilohertz sound output, stereo 44 kilohertz sound output. And we want to take all of this and we want to fit it inside this tiny package, or this one. And most importantly, it has to be powered parasitically. No batteries, no other cables. Every joule is sucked out of the DIN connector. Can't be done! Surely no one could build a fully polyphonic synthesizer in a tiny package that was less than 5 milliamps and has all of the features I just mentioned. I did it. I mean, obviously I wouldn't be making this video if I hadn't already achieved it. And as you can see, it's had a materials upgrade, a full metal housing, because as we all know, metal is better, and makes a fitting enclosure for the upgraded electronic gubbins inside. So ordinarily, you would plug this into your keyboard and then plug your speakers directly into it. In this case though, I've got a rather elaborate collection of splitters set up so that we can record it and see it on the oscilloscope and record my voice at the same time. The default patch, count the oscillators. You will have to take my word for it that the pitch bend is 14-bit. Unfortunately, this keyboard only sends a 7-bit bend value. If you know your synthesizers, you may recognize its first patch as a classic FM setup. We've got 2 operators and 2 envelopes per voice. The first envelope controls the effect depth and the second controls the overall voice. And in this setup, both envelopes are tied to velocity. But in FM synthesis, the thing to play with is of course the FM ratio. And we've got 2 controls for that, one for coarse and one for fine adjustment. And as usual, there is a low frequency oscillator controlled by the mod wheel. Or aftertouch. That about sums it up for the first algorithm, but there are multiple algorithms, so why don't you stick around while I twiddle some knobs? I've come up with something here a little bit like a Hammond organ, and we don't yet have drawbars. I could add drawbars. I may add drawbars. But in the meantime, I've added a parameter knob for each waveform, and in the case of the Hammondish waveform, it does a binary permutation through most of the drawbar combinations. So although polyphony is the thing we're going for here, I couldn't not add an arpeggiator. Aaron, my client, is very much into microtonal music. Now, I'm a novice when it comes to microtonal music, but Aaron is hardcore into it. He actually invented a microtonal keyboard. And MIDI, as we know it, can't really send microtonal stuff. The only way to detune a note is to use the channel-wide pitch bend amount. So on his keyboard, when you play a chord, every note is sent on a different MIDI channel, each with its own pitch bend amount. Well, this synthesizer supports that, but if you don't own a microtonal keyboard, the more conventional way to experiment with microtonal music is via tuning tables. So, I'm not one to shy away from a challenge. On this synthesizer, every note of every MIDI channel can be reassigned to be any frequency. Once again, I am not a microtonal person yet. I haven't got a clue what it's about, but just to demonstrate, here is 13 notes per octave. And just for fun, this one's a back to front keyboard. And the tuning can either be assigned on a per channel basis, or all of the channels can have the same tuning. It's completely up to you. It's a synthesizer. It makes a bunch of noises, and it makes them in tune. And this is by no means exhaustive. It's designed in a way that it can accept new algorithms. So if we wanted to add, for instance, a more traditional subtractive synth patch, we can do that. If I hadn't yet mentioned it, Aaron is planning to sell these. At the time of filming, I believe he is accepting pre-orders. So I'll put a link to his shop in the description. And that, my friends, is the demo out of the way, which is fantastic news because it means it's now time for my favourite part, the gory technical details! How the hell do you make something like this? Just what kind of black magic optimizations do you need to incant to pull something like this out of the bag? Well, before I reveal any tricks, let's take a look at the bit I'm most proud of. You can load new patches. You can load new algorithms. You can upgrade the firmware. You can load custom tuning tables. All of these are possible with minimal effort because of how I've implemented the bootloader. The number one question here is, why don't we stick a USB port on it? And the number one reason is aesthetics. To me, there's a certain beauty about a tiny package that turns DIN into TRS. If we had a USB port on it, well, for one, people would expect it to be a supplementary power supply, which means adding a mechanism to switch power sources that doesn't compromise on the parasitic power in any way. Not difficult, of course, but it would add to the bulk of the circuit board. And don't get me started on the ground isolation. We'd also want the USB port to act as a MIDI USB interface, and also have an automatic method of switching between the DFU and then the USB MIDI. And don't forget all of the physical difficulty of fitting a USB port into the design of the enclosure. All of this is doable, but it's tedious to implement, and at the very least it would increase the development time. So I said, forget the USB port. Right, so how else can we talk to the chip? MIDI sysx comes to mind, but let's just remind ourselves that MIDI runs at about 30 kilobits per second, and sysx encapsulates 7 bytes for every 8 cent. And the flash memory in our processor, well, originally it was going to be 1 megabyte. Sending 1 megabyte over sysx is going to take many minutes. But far worse than the fact it's slow is the fact it's unidirectional, which means there's no feedback, no acknowledgement. You don't know if it's finished writing a page, and you don't know if the checksum's matched. So all you can do is add delays, and when you get to the end of your 20-minute transaction, you may find it failed on the first byte, and you have to do it all again. So for me, MIDI sysx firmware updates are right out. But there's another problem that affects any bootloader that speaks the same protocol as the application. If the transaction is interrupted, if the memory is corrupted, then there's a risk that the chip ends up unbootable, or as some people say, bricked. There are defenses against this. The most common technique is to double the amount of memory you've got, and always keep a complete backup copy of the firmware image. But that's ugly. Remember that more memory means more power consumption. It's also a lot of work, and it still doesn't entirely guarantee that the device is unbrickable. The best defense against bricking is to use a ROM bootloader. The chip inside of here, spoilers, it's an STM32, like most microcontrollers in its class, contains a ROM bootloader. That is, it's a bit of code that cannot be overwritten, and it contains a multi-protocol bootloader triggered by a hardware condition. Given the hardware condition, sparing actual damage to the circuit, that bootloader will never fail to run. So I was looking at these two extra pins here. These are not used in the MIDI standard. They're there purely for future use. The middle pin is ground, and the other two pins are your current loop. So my thought was, could we make these two pins the differential pair for a USB connection? And I never did make up my mind about whether that would work. The problem is, what do you do with the 5 volts? Do you put it into the normal power pin? We'd have to add a 3.3 volt regulator and add it in such a way that it's completely off when the chip is powered parasitically. So what seemed like a fairly simple problem turned out to be a bit of a nightmare. But, if we go back to using a UART bootloader and we write our synthesizer so that its normal MIDI receive happens on the same UART hardware that the bootloader uses, they can share the RX pin. Then we've only got two things to add, the TX and the hardware condition that triggers everything. Conveniently enough, we've got two unused pins in the DIN connector. Now here's the clever bit. In MIDI mode, we run at the standard 31 kilobits per second, but when the bootloader is triggered, we can ramp up the baud rate as high as it'll go. And because it's now bidirectional, we've got acknowledgements and verification. For the production run, there'll be a programming box that you plug this into, but for now I'm just using this USB serial adapter. So this is not an active cable at this end. This end has a FTDI chip, but for this end all I've done is add one resistor and stick a DIN connector on it. You plug the synth in, you read or write your patches, you change the tuning tables, you do your firmware update, and even if you pull it out halfway through, it'll never get bricked because plugging it back in re-triggers the bootloader. Oh, by the way, this cable does not function as a USB MIDI interface. Well, it could do, but it would be terrible because these serial chips do not use the audio streaming class, they use the bulk transfer descriptors, which have terrible latency. Let's talk power delivery. So first of all, this whole 5 milliamp thing is a myth. The original MIDI spec asks for a 5 milliamp current loop, but we're not using the same return path. We're returning through the shielding ground, and because the MIDI spec asks for an equal split on the output impedance, they're both 220 ohms, then if we skip the return path, we've immediately got twice as much current available. Maximum power would be delivered if we made our input impedance match the output impedance, so that would be 220 ohms, and in that case we draw 11 milliamps. Now, I do know there is a 3.3 volt spec which compensates by having a lower output impedance, so that would let us draw more power, but the vast majority of keyboards use the old spec, so we have to go by that. If we've reduced our impedance, we'd get more current, but if we increased our impedance, we'd get more voltage, and voltage is important because our peak-to-peak sound output is going to depend on that. The quality of the sound output is going to depend on the stability of the power supply. And our processor it's not a resistor, it's a complicated changing impedance. So if we stray near that 11 milliamp number, we will get an audible buzz. We don't want that. This here is a ceramic capacitor, and this is also a ceramic capacitor, except this is one of the biggest surface mount ones you'll ever see, at 100 microfarads. Sounds great, but this type of capacitor is actually useless for our project. We use ceramics all the time for filtering and decoupling, and they work really well because of their low series resistance. But you may not know that ceramics have a much less desirable characteristic. Their capacitance is a function of bias voltage. There are different chemistries for different ceramic capacitors. Some of the newer ones are much better, but in general, as you approach the voltage rating, you lose more than half of your rated capacitance. If you want the smallest size and the best characteristics, the type of capacitor you want is tantalum. And something to watch out for on an electrolytic capacitor, the white stripe there, the polarity band, represents the cathode. On a tantalum capacitor, the white stripe represents the anode. Don't get them confused. Choosing a chip. I knew from the start I wanted to use one of the STM32L4 series, the ultra-low power microcontrollers, and if you've ever looked into this, you'll know there are hundreds of variants. We want the most processing power for the electrical power available. The number we're looking at is not milliamps, but microamps per megahertz. The current consumption is a function of how fast you clock the processor, and you can change the PLL settings while it's running, so as long as we're in the right ballpark, we can tweak the clock speed to match the power available. We want a chip with a built-in stereo DAC. That makes things so much easier. and a floating point unit with single cycle multiply. Surprisingly, that doesn't limit our search very much, so we just go for the chip that has the lowest power consumption of those results, which turned out to be, at the time of my search, the STM32L432. ARM is a strange architecture. ARM processors and the ARM GCC toolchain have evolved together like they're intertwined. Changes in the hardware reflected in the software, but also changes in the software reflected in the hardware. One of the things that sticks out to me with ARM microcontrollers is the ratio between RAM and flash. Older microcontrollers tend to have 32 or 64 times as much flash memory as they have RAM. Even like a desktop computer, I don't know what current specs are, but my slightly old laptop has a terabyte SSD and 16 gig of RAM, so that's a ratio of 1 to 64. But these ARM micros have ratios of 1 to 4. Relatively speaking, that's a huge amount of RAM. I think the reason for that is how you're expected to program them, using the toolchain they provide. They really don't want you to program in assembly. Everything is designed to work with their toolchain, and there is no support at all for bare metal assembly. Couple that with the fact we're doing floating point stuff, so tweaking algorithms and playing with sounds would get incredibly tedious if it was all VFPU instructions. So I submitted, and I programmed it in C, and immediately faced multiple situations where I said, if this was assembly I would just do X, but now I have to do Y, Z, U, V and W just to get the compiler to comply. In the most extreme case, I just gave up fighting the linker script and added a post-compilation step which modifies the binary. We've got limitations here. We've got serious limitations here, but they are totally different to the limitations faced by the designers of the Yamaha DX7. The DX7 had a quarter-wave log-sine lookup table. Quarter-wave because lookup tables were expensive, and they could generate the rest of the table by flipping and mirroring. And log sine instead of sine, so that they can do addition instead of multiplication, because multiplication was really expensive. We, on the other hand, have got bags of memory and a single cycle multiply, but what we don't have much of is processing power. The chip is underclocked for power saving, so everything that can go into a lookup table must. I'm not going to go through every optimization here, but let's just take a look at an example. Envelopes. So the classic way of doing this is you have a state variable. You say, am I attacking or decaying or whatever? And then in the hottest part of your code, for every sample of every voice, you ask, am I attacking? And if so, add something to my amplitude. And then you check, have I hit a threshold? In which case you switch to the next state. Now you can optimize this a little bit by pre-calculating the rate of change, but the clever optimization to do is to quantize the transitions so that they only happen at the buffer boundaries. The synth has a buffer. It's sending data to the DAC in chunks of 1 or 200 samples. So that's a tiny amount. That's every few milliseconds. If we change our envelope, if we do a trapezoidal approximation, just snap to the nearest grid line, no one's going to be able to hear the difference. But now, the hottest part of our code only has to contain amplitude plus equals delta. At some point in the future, I will probably stick the full source code up on GitHub, but there's a certain amount of cleanup that needs to be done before then. If you are planning to delve into that, then I hope you like function pointers. Now, for those of you still watching, yes, all three of you, here's the payoff. Let's take a look inside. I will state this is a development unit, so the production run probably won't come apart this easily. So there you go. The only way to squeeze everything in was to roll it up on a flexible PCB. You can't see very much, but the QFN microcontroller is at the bottom. The yellow thing's the main capacitor, and then there's a handful of passives dotted over the place. The wires leading to the jack are stranded gauge 36. When I first started writing my own synthesizers, there was something immensely satisfying about the process. It was like, not only did I write my own song, but I also wrote the software that generated the sounds in that song. Now, at that time, it was mostly playing around with the Web Audio API, which is about as high level as you can get. And though I later went on to write VSTs, that's still using the VST API, which is running on a platform that I didn't write. So, in a sense, this synth represents a level up for me. It's not only did I write the bare metal software, but I also designed and built the hardware it runs on. When I say I designed the hardware, what I mean is I selected the components and arranged them on a flexible PCB. But I didn't design the components. I'm still wholly relying on the ARM Cortex chip in there, and though I'd love to design my own processor, I don't think I'll be getting into custom silicon anytime soon. I've no doubt that there'll be newer chips available which draw even less power and can do even more processing, but the whole powered by MIDI thing may have run its course. I'm not saying the DIN connector is going to disappear, but any devices that do include it do so as a legacy option. It's all USB, and the ubiquity of USB does make sapping your power from the DIN connector somewhat hollow endeavour. So in some soppy sense, this little guy represents the pinnacle, the climax of my powered by MIDI adventure. It's my love letter to the DIN connector. The journey's not over yet, but it's been a hell of a ride so far.